what else is there to say? Yes, okay. Norman Verhelst, who is the presenter today, has very kindly offered to answer any questions that you might send to him afterwards, or if he doesn't have time to answer the questions during the webinar, then if you drop him a mail, he'd be happy to respond to you later on. Okay. So webinar today lasts 75 minutes. Norman is going to speak for 60 minutes, and then we'll take 15 minutes of questions at the end. I hope you can all hear us and see Norman as well. I'm going to turn my microphone and camera off now and hand you over to Norman. Enjoy the webinar.
Good afternoon, everybody. I hope you are all back from the first webinar and that you enjoyed. And here I'm with the things I promised for the first webinar, but there was not enough time, and I have to apologize for this. But this material is so extensive that's not possible to treat everything in 1 hour. So we go here, and I will not lose any more time with loose talking, and we go on. I hope I can, yeah. Here is an overview. I leave the overview as it is now. When you read the slides again, you can see what we will talk. And I immediately start with something that I planned to tell in the first webinar, but there was not time enough. But it's so important that I take it here again, because it gives you a good transition from classical test theory to IRT. And it is about a very interesting yet often ignored aspect of classical theory. Suppose an old test, which we call X, is replaced by a new test, which we call Y, and the intention of the constructors was to make Y to have the same construct measured as text I. But how can we be sure? Do X and Y measure the same construct? Can we find that? And a possible answer is, if they do, then if we administer both tests to a sample of students, then the correlation should equal 1. Yeah? Because if it does not equal 1, it's not the same construct. But there is a serious objection to that. What we observe, the scores of the students, is blurred, polluted, that we have discussed at the previous time, by measurement error. And these errors will suppress, and the a little bit old-fashioned word that was used in psychometrics for suppressing is called attenuate. So the correlation will be attenuated. And here is an example and a formula on how to use this correction for attenuation. It looks ugly, but I will explain it, and then you will see this very easy. The Greek rho stands for the correlation. Yeah. What we observe or can observe from our sample is the correlation between the scores on test X and test Y. We also are supposedly to know what the reliability of test X is and test Y. But what we would like to know is to see what the correlation would be if we could measure without measurement error. So it's the correlation between the true scores on the test X and the true scores on test Y. Yeah? And this formula says that you have to divide the correlation as you find it by the square root of the product of the two reliabilities. Here is an example. Suppose that the correlation between X and Y as you find it in your sample is 0.70. The reliability of test X was 85, and disappointingly the reliability of test Y is only 0.60. Then if we apply the formula, we have to divide 70 by the square root of the product of 0.85 and 60. And if you compute this, for example, with a pocket calculator or in Excel or whatever tool you use, you'll find that the correlation is 0.98, yeah, which is very, very close to 1. So we are quite sure that the construct measured by both tests is the same, yeah, although we find only a correlation of 0.70. It's very important that you are aware of that and that you try to use these formula because I often see correlations mentioned in articles or at conferences without ever referring to the fact that these correlations are between tests which are not completely reliable, because we do not have tests with a reliability coefficient of 1. They are all less, and this has an influence on the correlations that we see coming up from our data. So that's the good thing for classical test theory. But there are some weak points for classical test theory as well. The construct plays a minor role. Yeah? The central concept in the classical test theory is the score. And classical test theory does not say or gives you tools or means to say that if you have a reading comprehension test, that all items should measure reading comprehension. If you add an item on history and you say this item is an item of my test, then you will have the applicability of classical test theory as well as in the case that you do not use it. Yeah? Classical test theory does not treat the concept of a construct. It does treat the central concept in the theory is the score. A second weak point is that indices of difficulty and discrimination are population dependent. Yeah? Think about the item that we can present to grade 5 students and to grade 7 students. If these items have the same, are the very same items, they will appear to have a different p-value. So they are population dependent. And the most difficult thing is that comparisons of scores on different tests is very difficult and often impossible if you use classical test theory. Here is an example. At a university P, students of faculties A, B, and C take a test of English in March. And in May, students of 3 other faculties take also a test of English, but it's another test. Yeah? And then a legitimate question is, are the students of faculty A doing better or weaker than the students of faculty D? And it's very difficult to give a good answer. And be careful, do not just compare the scores, because the score in faculty D could be lower, but it is always possible that the items in the second test are a lot more difficult than the items in the first test. So this is a very central question, and classical test theory has a lot of problems in giving a rational answer to that question. So we speak of classical test theory, but what do we mean by a theory? Well, I have a quite simple idea of what a theory should be and what the structure of a theory is. In my view, a theory is a narrative about the observable world. When we have a theory, we aim always at saying something about the real world. And our building stones of our theory, the language that we use, consists of concepts and relations between concepts. Yeah, like in psychology, very old theory says that frustration is an abstract concept, causes aggression, abstract concept. Yeah? Aggression is not something that we can see. Aggression is a construct that we created. Yeah? And if we say frustration causes aggression, yeah, the relation is one of causality. That is our construct. And what we have to do is to clarify the relation also between the concepts and the observable phenomena. So we have to say what we mean by aggression, and we have to exactly define which phenomena fall under that construct and not. And sometimes this is very difficult and we run into problems. But the most important thing of theory is that it imposes restriction on possible phenomena. If we would say aggression is always caused by frustration, and that would imply that if we see aggression, that we are sure that there is some frustration. But maybe we can bring a student or a person in a condition where he's not frustrated and yet see aggression, and then we have a problem, because we have said You will not see aggression if there is no frustration, and sometimes we see aggression without frustration. So something happens that is not foreseen in our theory. Yeah? So our theory is falsifiable. We do predictions, what we will see in the real world, and if we see other things which we did not predict, then our theory is falsified. And the problem is that classical test theory, in my view, is not a theory in this sense, because it's more of a tautology. It says your observed score is what you will earn on the average plus something more or less. Well, this is so trivial. It's always true that it is barely worth a theory. So it's a poor theory. It's a, we will say in science, we say it's a very weak theory. And we now will go to a stronger theory, and we will start with Gutman's scalogram, yeah, which is a kind of prototype of IRT. It's developed in the, I think, the 40s, 1940s. And there the targeted concept is very central. The concept itself, like ability or competence or an attitude, is represented by a line. Yeah? So it's a continuous variable. And if we say a line, that means there is no bound. People can have a measure of running from minus infinity to plus infinity. This is very important, because the difficulty, for example, in classical test theory cannot run from minus infinity to plus infinity. It can only run from 0 to 1, so it's bounded. The target concept here is an unbounded variable that can take all values possible. And another very important aspect of Gutman's scalogram theory is that persons and items both are represented by points on the line. So a person is a point and the item is a point. And the purpose of measuring is to find where the point of the person belongs on the line. And the relation between these points is this one. Yeah? It is such that the observable responses, a yes or a positive answer, a correct answer, reflect the ordinal relationship between the points, person, and the item on the underlying line. And the line itself, the variable, your competence, is non-observable. Yeah? The score is observable, albeit with a measurement error. Here we say that the concept that we want to see is non-observable. It's latent. Yeah? And therefore, an older name of IRT is latent trait theory, but this name is not used very much. Here is a graphical representation of Gutman's theory. If you look at the upper graph here, I represents an item, and the dash here represents the position of the item on the real line. And now we see that for all persons being to the left, they have the same ordinal relation to the item, they are left to it, or their number is smaller than the number that belongs to item I. These persons will give an incorrect answer. And if persons are to the right of the position of the item, they will give a correct answer. Okay, so this is the relation between the concepts and what we can see, because we can see the answers of the subjects. What we have to find out is to infer, to find out where the person is related if he or she answers to the items. Well, you see that if we only have one item, well, we can partition the population in two parts, those who are to the left of point I and those who are to the right of point I. This is not too interesting, but it becomes more interesting when we have more items. Now here at the bottom we have a position, the situation with three items which are in the order I, J and K positioned on the real line. Now if you look at a person who is very far to the left of point I, he will have three items incorrect, because if he is to the left of I, he is also to the left of J and also to the left of K. When we follow that person in his development, he will end up here between the positions of I and j, and then he will have item I correct and item j incorrect. Yeah? And in the same way, if he moves further on and passes beyond j, then he will have I and j correct and k incorrect. And finally, when he's far enough to the right, he will have all three items right. But, and this is so important, yeah, we also incorporate things which may not happen, which should not happen, yeah, because you cannot find a point on the real line where you can have the answer 1, 0, 1. So that is a point which is to the right of I, to the right of k, but at the same time to the left of j. That's not possible on a single line. So we say that if this is how the world works, we should only see 4 different answer patterns, while there are 2 times 2 times 2 is 8 possible patterns. So of the 8 possible patterns, only 4 will appear, and not arbitrarily 4, but 4. So let's have a look, another look. If we have 4 items, I, j, k, and m in that order on the line, people far to the left will have all items incorrect. People have 1 item correct, it will always be the item I. If they have 2 items correct, it will be I and j, etc. So this triangular pattern is called by Gutman a scalogram. And our duty as measurement people is to find the right order of these items on the line such that this scalogram pattern appears. If we have 4 items, we have 16 possible patterns, but Gutman's theory say only 5 will appear. If we have n items, the number of possible patterns is 2 to the n, but the number of allowed patterns is only n plus 1. Take an example, take n as 10. If I have 10 items, 2 to the 10th is more than 1000, it's 1024, and Gutman says, yes, 1024 are mathematically possible, but you will only see 11 different ones. So this is a very, very strong prediction. And if it is not true, well, then you are in trouble because your theory is falsified. And if we tell that to Gutman, that in all the data sets that we have seen, his theory is falsified, he has nothing to say. That maybe he personally could say something, but there is nothing in his theory that allows for such a violation of his principles. Yeah? So this is a very vulnerable theory. And now we will look at this theory from a slightly more extended point of view and see why this theory is so vulnerable. Yeah. And here is the same thing. So on the x-axis we had the latent variable, yeah, and now we will look for any position on the latent variable, so any position of possible position of a person on that line, what the probability is that he will give a correct answer. So if he is far to the left of the position of the item, which is here at the vertical line, that's the position of the item, the probability is 0. And if he comes closer, the probability remains 0 because Gutman says he will for sure have this item incorrect. Yeah? Even if he's very, very, very close to the position of the item, the probability is still 0. He will have the answer incorrect. And then suddenly, if he's a little bit further, then Gutman says, and now with the probability 1, he will always give the correct answer. Yeah? So this model is deterministic. It does predictions in never or always. And this is dangerous because if you say never and always, you're very vulnerable. And I can just do some sabotage and generate an unexpected answer, and you have no answer. Your theory has nothing to tell me or to defend itself because it was a little bit too arrogant. Yeah? But there are other things which are very nice. If you look at the line and just not look at the jump, the dashed line here does not belong to the curve, it's just there for visual support. Yeah, we see that the line is not decreasing. So It starts at 0 and then suddenly it jumps to 1, but it never goes back to 0. How far you might go. So we say it's non-decreasing, but it's also in mathematics very important. It's not continuous. It's a step function. It has a sudden jump. So the dashed line does not belong to the curve. Yeah? It jumps suddenly from here to there. And working with step functions is usually a little bit difficult in mathematics. Now we have to do some mathematics, a little bit of algebra, and I will skip most of it. The only thing that you have to remember is, you know what exponentiation is. That's taking a power. 3 to the 5th times 3 to the 7th is 3 times 3, 12 times, yeah, and we can write that as 3 to the power 5 plus 7. Yeah. What I give here, but I will not go through that because for lack of time, you have to remember that for any positive number c, and in the example c is 3 here, it holds that if you have c to the power 0, the outcome is 1. That is what we will use a little bit further. Then we have to tell something that probably most of you know, but maybe not. In mathematics, there are numbers which are so famous that they have their own name. And there is such a number, and it has the name E. So it's just a letter, but it's the name of that number. And it's a number that we cannot write down exactly because it has infinitely many digits, but it's a number between 2 and 3 is about 2.718. Yeah, if you remember that, that's okay. It's between 2 and 3. And then we have also something where that number E is used, and that's the exponential function. Yeah, and the exponential function is a rule. It says the value of the function y is the number E to the power of x, and x is the argument. And we will have a look, and I will also download or upload the Excel file that I will use and show you here, because there are other things as well. Here is the exponential function. So what I did, I chose some values of x. They are running from -4 to +4. Yeah. Excel gives you for free the exponential function, so I computed the exponential function and I made a graph for you. And we have a look at the graph and see some important things. We see that if we start from 0, e to the power 0, remember e is a number, and a number to the power 0 equals 1. Here it is. If the number is 0, the value of the function is 1. If we start from 0 and we go left, so take negative numbers ever smaller, we see that the function, if you follow it, is just like a plane landing very smoothly. And this is important. It lands, but in contrast to a real plane, it's a plane that never touches the ground. So it goes down to the x-axis, but it never touches the x-axis. So however small x the argument is, the exponential function is always positive. It is never 0, and a fortiori it can never be negative. Yeah. But if the argument is positive, we see that the function is going up very fast. Yeah? Because for 4, it's already more than 50, and if x is 10, it's really very big. So this is the exponential function, and we will need it in a bit more. Okay? Now we use the exponential function to build another function which is called the logistic function. And you see that the logistic function is also using the exponential function, but it uses in its fraction. The numerator is e to the x, dus to the argument, and the denominator is the same exponential function plus 1. E of x is always positive, and a positive number plus 1 is larger than the original positive number. So the denominator is always a little bit larger than the numerator, and that means that f of x is always, the function is always bound between 0 and 1, because the denominator is always larger than the numerator. Another way of writing this, but it means just the same, and I go back to the first one, you can write the number e to the power x, but sometimes we write it also like y is, and we write exp of x, and that means just the same thing as the number e to the exp. Yeah. So also for the logistic function, we can have two ways of writing this. We will use the second one, and you will see why that is in a moment. Here is some verse to help you to remember what the logistic function is the x of something, yeah, the x here, divided by 1 plus the x of the same something. So we have here and here the same thing, but in the denominator we add 1. The something is called the argument of the function. Okay? Now we go to IRT back, because in IRT this logistic function and some variations that we will see in a moment are very, very popular, and there are several models that use the logistic function, and we will start with the simplest one, and the simplest one is known as the Rasch model. Rasch was a Danish mathematician who developed the Rasch model. That means the model is named after him. Yeah. What we need in a item response theory is an item response function, and now you have to pay very well attention. The item response function, we use the symbol f, yeah, but we give it a subscript or an index I. That means that for every item I, we will have such a function. So there will be as many functions as there will be items. And what is the meaning of that function? Yeah, if this function is, for example, 0.50, that means that the probability of the score of item I having the value 1, that means the probability of a correct response on item I, given the value of theta, is 0.50 or as much as f gives. Okay? Now, in the Rasch model, we say that the function looks like this. You see, it's a logistic function. It's the x of something divided by 1 plus x of the same something. And that something now is not theta, it's theta minus beta I. And we see that this index here, I, is reappearing. It's the same as the index I there. That means that beta I is specific for item I. Because we have a subtraction, it must be a number. You cannot subtract chocolate from a other number. You have to subtract numbers from each other. Theta is the value of the latent variable, and beta is a number that belongs to item I. And we leave it for the moment being non-specified. We don't say that it is 0 or a half or -2 or so. It is some number. And so it's a non-specified number is called a parameter. Okay? Now we will have a look at this in the next slide. Yeah, I have repeated here the item response function in the Rasch model. So theta stands for the symbol for the latent variable. And we know that theta can assume values from -infinity to +infinity. And we will compare the theta value to beta. And comparing means, in this case, making a subtraction. Yeah? And the difference can be positive, or the difference can be 0, or the difference can be negative. Yeah? Since we have here item-specific number, each item has its own function, but the difference between the function is only in the number of beta. Yeah. Now, look what happens if theta, the value of the latent ability, equals that value beta I. Then the difference is 0. And remember that here, if the difference is 0, we have in the numerator x of 0. And x of 0 is 1 because it is the exponent of argument 0 is 1. Yeah? So in the numerator stands 1 divided by 1 plus, and again 1 here because this x is the same thing. Yeah? So we have 1 divided by 1 plus 1 is a half. So now we have a beautiful interpretation of beta. Beta is, and I say it with something which is maybe not good English, the amount of ability needed to grant a probability of exactly a half for a correct response. Meaning, and we will see that in a moment, meaning that if your theta is smaller than beta, then the result is negative, that then the probability will be smaller than a half, and if your theta exceeds beta, then the difference is positive, and then your probability will be greater than half. Yeah? So the more ability is needed, yeah, the more difficult the item. Yeah? And therefore, beta I is called the difficulty parameter. Now let's have a look at the Excel file again, and I have also made a picture of yes, here it comes. Yeah, so this is the logistic function. Yeah, and you see that the logistic function remains also positive when we go to minus infinity, and it goes up, always up, but it never reaches the value of 1 if the argument grows to very large values, and it is S-shaped. That's the logistic function. Okay? Let's see where we are. Here is an item response function for an item with difficulty parameter. Of course, I cannot draw all values from minus infinity to plus infinity, so I just cut them at minus 3 and plus 3, but the curve is going further and further up to approaching 1 if the argument is large, and goes down to 0, but never reaching 0 if the argument is, yeah. And then we say the difficulty parameter is 0.75. I have drawn this for you. If on the vertical axis we have the probability of a correct response. If the probability is 0.50, we look for the corresponding point on the y-axis using this curve, and we find 0.75. Okay, this is what you can do. I have made for you a tool that can help you to make these pictures and to see what happens, and it's also in the same file, and it's here in the page Rasch, and it plots for you at the same time two item response functions for 2 different items. The parameter values for the beta are given here in blue, and at the left hand side you have a grid of values of the ability, which we call theta. Yeah? And here is a formula that you can see here in the top window. Yeah? Do not erase these things or your picture will tend to disappear. So leave these numbers because they are the result of a formula. What you can do is to change the numbers here to see what happens. Let's change this one to 1, for example. Yeah, but you have to leave now the cell where the number is. So if we put it here, and we see that now for this item the parameter is 1, because for a theta value of 1 you have a probability of 0.50. So the picture is dynamic and it shows you what happens. What is important here is that all these curves have the same form. They only differ in position. So the blue one is just the red one, but shifted to the right from minus 0.25 to plus 0.75. So 1 unit shifted to the right. That is what you can do. And we will later on see other tools for more complicated models than just the Rasch model. Okay, so here you have these two, and I have put the values here, but you could see them in your Excel file. Now, what we have done now, and this is important, I have told a story, but the story is my narrative about the world. I think, if I am a proponent of the Rasch model, and let's do as if I am for today, my narrative say how an answer to a test item comes about. I say, yeah, people differ in ability, and depending on the ability, they have for each item a specific probability of having the answer. And you see already the difference with what Gutman say. Gutman say, if I know your position relative to the item position, I know your answer. But we are more careful. We say, we do not know your answer. We remain insecure about it, but we know the probability. So if I have such an item and say, I can construct 100 different items with the same parameter, then if the probability, depending on your ability, is 0.25, if I give you these 100 items, you will have a probability of 25 for each, so your expected score is 25. Yeah? That is what I predict. And the question is, and we will see that, yeah, we have a narrative, a hypothesis. We say, this is the way that answers come about. Each item has such a curve, and each person is a point on the horizontal axis, and that determines things. Yeah. That's what we have. We have a story, and we have our data. And it's important that you have a look at the data file, and here is one. Yeah, it's for a reading test that was given in a very gentle way to me by your exams in Budapest. Thank you, Zoltan. If you are there, I still use the things. You only use them for didactic reasoning. This is a test of 25 items, and you see I have a big table. It starts here. Yeah, I have a big table of ones and zeros. That is the summary of what I have observed. Maybe I could observe more things, but usually that's what we look about. So we have a story, and we have such a thing. Yeah, you become completely dizzy if you look at that, and maybe you don't know what to do. Well, that is one of our tasks. We have to do something sensible with that. Let's go back here. So we have as yet quite complicated story about how the world works, and we have here realizations of XVI. XVI is the answer of person V on item I. I have rows representing the persons, I have columns representing the items, and every answer of person V to item I is either a 0 or, and this is a typo, which I will correct immediately, which is either a 0 or a 1. That is what we have. And what do we have to do? Well, we better structure it. Yeah? And usually we start by estimating the parameters. And the parameters in the first place are the item parameters. And we need that because if somebody comes at your doorstep and he tells you a story, be careful, because it could all be lies. So you have to have a reason and convincing arguments to believe that story and to trust it. So we have to find methods to check our narrative, to see if this is trustworthy. Yeah? And then comes an important moment, and you should not forget that. You have to either to accept or to reject your narrative. And that reject is a little bit relative, because it might turn out that you have to reject it not because your whole test is useless, but because there is one bad item. So you could say, oh, I'm sorry, we will try again with this funny item removed, and maybe we will have better results then. But in the end, you will have to come to a definitive judgment. You accept what is left of your test, or you reject it altogether. But be careful, if you reject it altogether, well, you have nothing, and collecting data and having people to make your test is, well, there is finance involved, and you have to be careful of that. And once you have done that, yeah, and you have accepted it, yeah, then you can use the test. And you can use the test on your sample, but don't forget, you can also go and measure. You can use your measure instrument that you have constructed to measure other people. This is, for example, what is done by intelligence tests. Intelligence tests are made, and we use the data of a sample of students to have insight in the features of our test. And if the test is accepted, then we go out in the world and we measure a lot of people, and we say how intelligent they are or how intelligent they are not. Okay, so we will have a look at some of these things. I will not go on the go and measure aspect, because that would take us a lot too far, and it's statistically a little bit complicated. So I will have the parameter estimates, the checking of your narrative, and what you could do to improve the situation a little bit. Parameter estimation. Parameter estimation is technically a difficult problem. In the 80s and the 90s, I was busy in that stuff. That has cost me tears and sweat, and it was really very difficult. Yeah, there are several methods to estimate parameters, and there is still a controversy about some methods, but it's a little bit difficult to give details on that to a non-technical public. Yeah. The non-technical user can nowadays use public software, but beware, and beware is followed by 3 points. And my point of view is, even if you do not understand it, if you publish things, you are responsible for everything that you did with your data. You cannot say, oh, but I have used a software that I do not understand, and so if it is wrong, it's not my fault. That's not the way it goes. If you are working in science, you are yourself responsible for everything that you write down. Yeah, I cannot discuss it in a technical way, but in general, and I work together with a number of language testers, it shows the necessity of interdisciplinary cooperation. Yeah, it's a profession in its own. Making good tests is also a profession in its own, and we cannot be experts in every field. So if you want qualitatively good products and good results, you should look for interdisciplinary cooperation. This is my message, but it's not the end of my talk. Okay. What about checking the narrative? The checking of Gutman's model and his theory is very easy. It was enough to find one single counterexample, yeah, and his theory was gone because he was too deterministic. But our model is probabilistic. We do not claim to know what people will answer. We only claim that there is some restriction on the probability of an answer. And testing is not that straightforward. Often statistical tests are used, and I will give an example without being too technical, yeah, but we have to understand the logic of a statistical test, yeah, and graphical aids are sometimes helpful in understanding that, and they are also helpful in seeing if your narrative is okay or why it is not okay. And I give you an example. Here there is a graph, and it's about the reading data I got from Zoltan, and it's about item 4. So what I did, I used the Rasch model and I estimated all parameters. Once I have a good value of all parameters, then I can say, if you are very weak, then I know what the probability is that you will have this item 4 correct. And this probability is given here by the point on the blue line. But of course, if I know who the weak students are, and I know who the weak students are because I can find them in my data file, yeah? If they are weak, the total score will be low. So I have made a number of groups, yeah? And the first group is the people with the about 10 to 15% lowest scores. And then in that subgroup, I can find the proportion of correct answers to that item. And that proportion is given here by that red bullet, which is about 0.20, okay? Because my x-axis always runs from 0 to 1, and the dashes indicate 25%, 50%, and 75%. So in that weak group, about 20% got the answer right, while the theory says that only about maybe 13% should have the theory right. And so we can do it for all groups. And what we see is that the points that we predict and that we find here do not correspond very well. Now, ideally, all the points, all the crosses or bullets should be laying on the blue line. And we see that they are deviating from the blue line. And is this deviation serious or not? Well, the two gray lines here around the blue line form a kind of envelope. And it says that in 95% of the cases, all the crosses or the dots should lie between these two gray lines in the envelope. And we see that they don't. 4 are outside. And we also see that there is a systematic pattern, because the ones for high scores are below the envelope and the ones for the low scores are above the envelope. So that means that if you think of a fluent line going through all the crosses and the bullets, the line is flatter than the blue line. The blue line is steeper, and the empirical line is flatter. And if a line is flat, then the difference in success between the strongest people, here about 75, and the weakest people, about 20, is less than the difference as predicted, because this one here is about 80 and this one is about 12. Yeah, so we cannot as well discriminate the strong people from the weak people as not as well as the theory predicted. So that means that this item discriminates less well than predicted by the model. Okay? That is what these things do. Now, this analysis is based on a sample of about 1,330 people. What I did then is to take from these 1,330 a sample of 100 students. Yeah? And I did the same analysis, and here is the result. So this is the picture of the same item, and what do we see now? Yeah, that there are no bullets anymore, and the crosses there are less, and that's because also our total sample is less. Yeah, we cannot make that many groups because the groups have to have a substantial number of persons. So we have only 3 groups here of students, and we see that there is a deviation, but the deviation well falls between the boundaries given by the confidence envelope. So from this picture, we cannot say that there is clear evidence that our predictions are wrong. Yeah? This is something that might be caused just by accident. Yeah? While here, yeah, we have clear indication that this is not good with this item. And how come that we do not have? Well, it has to do with what we call the power of the statistical test. Yeah. The probability that a deviation from the model will be discovered, so that the discrimination is higher or lower, yeah, is dependent on the seriousness of the deviation, because this one, the empirical one, is flatter than the predicted one, but it could be more flat. It could be, say, almost horizontal. That would be a far more serious deviation. Yeah? But we don't know that beforehand, and this is the deviation that we have. And it is the probability that you will find this, yeah, is dependent on the sample size. Yeah? And what we see here is that the confidence envelope is narrower because we use, in this case, a total sample of more than 1,300 students, while in the simple case, we use only 133 students, only 10% of what was available, and we have a lot less power. This probability of finding that something is not okay is called the statistical power. Yeah? And the deviation is discovered means that we will have a significant result in our statistical test. In everyday language, yeah, we say it's a probability that the alarm bell will ring. Yeah. And the deviation here has to do, and I told you that already, with the difference in discrimination. Okay, so we have to look a little bit closer to our narrative. It's just not pictures, but we have a number of very strict assumptions in the Rasch model, and I have listed 3, and they well indicate that this is the Rasch model. The Rasch model say that all items discriminate equally well. Yeah? That the latent trait is unidimensional, and here it comes again. I told you that some weeks ago, that there is a kind of independence, and it's called local stochastic independence, but I will explain you what is meant by that. Yeah. In most software, and this is important, the statistical tests have little power if unidimensionality or local independence are not true. So we have to be very careful on that. All software offers you a package of statistical tests of goodness of fit to see if your model is okay or not. But all these tests only will discover deviations from the model in that way. So it's relatively easy to find if discrimination of an item is better or worse than predicted by the Rasch model. But if the items, the latent trait is not unidimensional, or if this independence is not true, then it's far more difficult to find. And then you say, well, then there is no problem.
Excuse me,
yeah, of course. Yes, please.
Yes. Yes, I'm very sorry to interrupt you. You've got about 3 or 4 minutes to finish off. If anybody would like to, 3 or 4 minutes.
Okay.
Okay, and if anybody would like to write any questions, then please write the questions in the question box, and
Yeah.
I'm sure Norman can answer a few of the questions.
Yeah.
Yeah, so maybe a couple more slides. Yeah.
Yes, the independence is quite well explained with full sentences in the slides, but I want to say a word on multidimensionality. Yeah, multidimensionality. Say we have constructed a test on communicative competence and that contains reading items and listening items. Probably you will say, yeah, but these things are not the same. Then the best thing that you can do is to make a reading test and a listening test and treat them as two different tests. But now in example 2, you have a reading comprehension test consisting, say, of 6 text fragments of 5 questions per fragment. Yeah? In a fragment about history, yeah, people who know a lot of history and are interested in history, so are more able in history, will probably be helped to give the correct answer over and above the power they have from their reading ability, and they will do better than people with the same reading ability but who are not interested in history. So there is a second dimension, and the second dimension is there just for these 5 items belonging to that same text fragment. Yeah? And a testlet or a task problem is a set of items belonging together, for example, a matching item or a text fragment, and one can avoid the influence of lack of independence or multidimensionality by considering the testlet as a partial credit item instead of as a collection of binary items. And the model that we have to use for that is a beautiful model, yeah, and it's called the partial credit model, where we can have scores 1, 0, 0, 1, 2 to some number m. If the Rasch model m is 1 and we have 1 item parameter, if the PCM we have a maximum score of m, then when we have m parameters. In the Rasch model we compare theta to beta. Here we have for score 1 we compare theta to beta 1 of item I. For score 2 we compare twice theta to the sum of the first 2, etc. In the next slide you have the formula. If you do not understand it, just skip it. Here is the category response functions for the Rasch model. The going up is for category 1, the correct answer, and the one going down is for category 0. Why don't we plot these? Because they are redundant. The sum of the 2, if your probability is 0.25 for a correct answer, then the probability of an incorrect answer is 0.75. It's just a complement. So we don't need the complement. Therefore, if you have binary items, we usually give a item response function for category 1. But we could as well have given the one for more categories. If we have category response functions in the PCM where m is 2, the maximum score is 2. For the first category, the curve is going down. For the last category, the curve is going up. And for the middle category, is going up and then down. And the parameters are the at the crossing points of the 0 and first, and of the first and second one. These are your thing. There is also a tutorial here for 3 categories. You can choose the blue numbers, which are the category parameters, and the program will automatically adapt your picture. I have to be quick. I'm almost done, Peter. Just don't hurry me. The big advantage of IRT. The big advantage of IRT is that performance on different tests can be meaningfully compared. If the tests measure the same construct, if they are calibrated, that means if their item parameters are calibrated together, are estimated together, and if they have items in common. This you have to need to use anchor items with very complicated designs. This is not simple, but the idea is there. Yeah. Partial credit items and binary items can appear in any mixture, but IRT is not the ultimate salvation. Suppose I have a test and I have very, very strong evidence that the Rasch model is valid, and here are my 3 item response functions. You know, what it says, for example, is if your theta value is at -2, you have a probability of about 0.25 or 30 to have the first item correct. This statement can be true, but it does not follow, it does not imply that there exists a human being with a theta value of -2. The Rasch model says nothing about that, about the existence of such people. Now assume that the Rasch model is true, but that the theta values are show very little variation, and they are here where the fat line is depicted. So what will happen with this test in our population with a very small variation of the theta values, yeah, well, we will see it if we zoom in on this picture, what I have done in this thing. And what you see here is that in your whole population, if you are the weakest person having a value of -0.1, or you are the strongest person having a value of +0.1, you have almost the same probability of having the item correct. Yeah? That means that your expected score, your true score is your expected score for the very weak persons, and for the middle persons, and for the very strong persons will be about the same. So I will have a very small true variance of the true scores. That means my reliability will go down and it will be very close to 0. Yeah? So that means, and this is what you should realize, the validity of the Rasch model, so the Rasch model is true, does not imply that one has a reliable test. And so the circle is closed again. Don't throw with IRT, and that's what I often hear. People say we have IRT, so we don't need classical testing. Yes, you do. And you have to check the reliability of your test. And I'm not impressed by people saying the Rasch model is valid for me. I'm more impressed by a test with a good reliability. So think about it when you are trying to understand what is done in IRT. This was what I had to say. It was a little bit fast in the end, but you will have the opportunity to read in detail what I have said here. Thank you very much for being here. I will have now a look at your questions.
So, Norman, at the moment we don't have any questions.
You don't have any questions?
So, unless there's a problem with the question box, which I hope there isn't.
Oh.
So if you'd like to summarize further, or just go back on talk about something that you talked about earlier, but perhaps didn't spend as much time on as you'd like to have done.
Yes, just please. Yes, I will go a little bit back. Sorry, I see only my own face, and yeah, I will give you something on local independence. Here is something on local independence. Oh, yeah. Now, let's see this to explain that. Suppose that I study in developmental psychology a population of children in the age from 6 to 14 years old. And I have made 2 tests. It's a bit ridiculous, but it's the purpose of being ridiculous here. Test X is the size of their feet. This is a test and everybody has a score. Probably it's quite reliable. Maybe it has a reliability very close to 1. And test Y is the score on a reading comprehension test, which is the same test for all students in the sample. So I collect a sample of students, both measures, and I compute the correlation. What will the sign of this correlation be? Will it be negative? Will it be 0? Or will it be positive? And you can guess, of course, but you have to tell me why. Yeah. Maybe people think 0 because size of the feet and reading comprehension, even if it is spelled with an error, yeah, are things which have nothing to do with each other. But they are wrong. The correlation will be positive because the older the children, you see, this was in a hurry, the older the children, the bigger their feet. And the older the children, the better they read. Isn't that a nice verse? Yeah. And that will cause, because I have quite a variation in age, yeah, that will cause the correlation between the size of their feet and their reading comprehension test score. Yeah, and we will find a positive correlation. But you also immediately see that the variation in age explains the correlation. This correlation is there not because there is an intrinsic relation between the size of your feet and your reading comprehension. You don't read with your feet, at least I hope you don't think so, but it's because there is a third variable that explains the correlation. Yeah? And how could we prove that we are right? Well, we take a subpopulation of children of the same age, children of 7 years, children of 9 years, children of 11 years, and we compute there the same correlation, and we will see that the correlation will vanish. It will be 0. So if we look locally at a value of the explaining variable, which is the age, yeah, we see that the correlation is disappearing and it reappears, and that is because the age is not constant anymore in the total population. So the correlation is there because people, the children have a different age. That is the explanation. Now we will follow the same reasoning for in IRT, local independence. Yeah. In an arbitrary group, say a class of students, yeah, if you compute the correlation between the answers on item I and on item J, you usually find that this correlation is positive. So the correlation, the symbol rho, between xi is the score on item I, xj is the score on item j, that this correlation is bigger than 0. Yeah? But if we find a population of students with the same value of theta, yeah, then this correlation is 0. So we say the correlation between x and y, given that theta is taken constant, is 0. And this is an assumption. Yeah? And we have to assume that, otherwise we cannot do sensible mathematics with our narrative. Our narrative is full of formula, and we do a lot of algebra on that. And if you learn the profession of a psychometrician, you have to learn on how to do all these exercises. But the exercises are only possible if you have such an assumption. Otherwise, you are in very, very big trouble. Yeah.
Okay, Norman.
And you have to.
I think we need to...
Yeah, I stop in a moment, Peter. And the test out to find if this hypothesis is tenable is very difficult. Yeah. So, and what you can do then is to, if you have suspicion that the local independence is not true, and it is not true in a task like in our, if you remember from the first time, our multiple matching task. Yeah, remember that if Tallinn is assigned to Portugal, you say Tallinn is the capital of Portugal, then by necessity the probability that Lisbon will give the correct answer is 0, because you have used Portugal already. So that, but this is a very complicated pattern of dependencies. Therefore, it's better to use such a task not as 4 items, 4 binary items, but just to count the number of correct responses in this task and to treat this as a partial credit item. Yeah? So in this way you can circumvent the trap of lack of local independence. So I think I will have to stop now and you can read things. You are also allowed to write to me if you have problems. I will try to help you. But if you say, can you write an article for me that I can publish under my name? And the answer will be no. I thank you very much for your attention.
Okay, thank you ever so much, Norman, for that. Yes, and just to reiterate, yes, Norman's very happy to answer any questions in writing. So when I send around the link for the recording, I'll also send around his email address if you don't already have it, and I'm sure he'll be willing to spend his weekend answering your questions. Okay, I think that's it for today. There will be one more webinar in this series, as I mentioned at the beginning, which will probably be in April. So we'll keep you posted about the topic for that and the date and everything. So in the meantime, thank you very much for your attendance. Thank you again, Norman, very much for an excellent webinar. And Happy New Year to everybody.
Okay. Bye-bye, everybody.
Bye.